So, let's get started. The homework, if it comes.
Should all the initial conditions be for time 0, everything starts at 0?
If everything is assume as 0. Okay. That goes for exams, any homework. If it's not mentioned, initial condition is always 0. Any questions? All right. By the way, if you have any questions after class, if I'm not around here, I'll be in my office in Keller Hall, 6177. It's on the Canvas page. If my door is closed, just knock. That's absolutely fine. If I'm inside, I'll just open and we can chat. If the times I'm in the office does not work out for you, just send me an email and we can meet on Zoom. So last week we looked at the mechanical model of our motor. And this is the standard model that we are going to carry throughout, irrespective of what motor we are going to be looking at. It doesn't change. And we did look at other conditions where we could have torsional coefficient, the spring constant. Those are all things that we're going to ignore going forward. So this week, we are going to look at the second part of the prerequisite. So we are going to be looking at the black box that we used, how the power converter works to generate from 40 volts DC bus that we have to any voltage between 0 to 40 volts plus 40. Okay, so that's the objective of today's lecture. Looking at the poles, looks like a lot of you haven't had experience with the power electronic converter except for 3 or 4 of you. Most of you mentioned you do not know how a buck converter operates, so we'll go into a little bit of detail and try to figure it out. We won't worry ourselves with the semiconductor physics of it that you typically learn in a power electronic course or another semiconductor physics course. Or if you're taking the advanced power electronic course this semester, the instructor Atul Jasi will be handling that as well. Right? But in our case, we just want to figure out how to use these switches to generate this voltage range that we want so that we can rotate our motor in whichever direction, create sinusoidal voltages, create DC voltages, whatever we need. Right? So let's start with a very simple example we looked at last class itself. We had a 10 volt DC bus. We had a switch. And then we had our inductor, let's take 10 millihenry, and let's say a 1 ohm resistance. And we looked at what the response of this is going to be. So the current, again, at time t equal to 0, I don't have to give the initial condition. If the switch is open, current is going to be 0. It goes without saying for this case. So the response is going to be V by R minus 1 minus V bar minus T by tau, where tau is the time constant given by L by R. Right, so we substitute those values in this case, it comes out to 10 minus 1 minus T bar minus T divided by tau, and tau itself is going to be 10 seconds, right? Sorry, 10 milliseconds. Whatever. So this is the amount of time it would take for the current to go from 0 to 6.32 amps, right? In the time it would have reached that particular current. Or if it started raising at the rate at which it was raising at time t equal to 0, by this time it would reach the steady state value if it raised at that rate, which it can't because of the presence of inductor. Right? Any questions? Okay, so here comes the problem. Let's say the current has reached steady state or very close to steady state once the switch is closed. Okay. Let's say after some time t for a long period of time, it has reached steady state, and then we want to open the switch. What is going to be the problem? Is there going to be a problem if we try and open the switch?
The inductor is carrying a lot of current, and it's hard for that to change.
Right, okay. So the inductor is carrying 10 amperes current at time t equal to infinity. This term would have gone to 0, so the inductor current is going to be 10 ampere. And let's say this is a mechanical switch of the sort that we have here. I can swap it. Let's say the contacts break in about a millisecond. So the time it takes for the current to extinguish from 10 to 0 ampere, let's say for this mechanical switch is about 1 millisecond. Not an unreasonable assumption. Between 1 to 10 milliseconds is a very reasonable value for a mechanical switch, mechanical contactor. So the voltage across this inductor, when I break this contact, is going to be equal to L di by dt. So assuming it's all transitioning linearly, can convert the differential into deltas. We have 10 millihenry 10 to the power minus 3 times the current went from 10 ampere to 0 ampere. I'm making a mistake here. If somebody can point it out, that'll be great. It goes in a period of delta t of 1 millisecond, and that value comes out to 10 to the power minus 3. There's this cancels, that comes out to 100 volts, right? There's one mistake I made here. Anybody want to point out? So when I close the switch, what is going to be the polarity of the voltage across the inductor? So from the current, we can say what the voltage across the resistor is going to be, assuming this to be positive, this to be negative. The voltage is just going to look like this, right? Since it's 1 ohm, it's going to reach 10 volts at steady state. So this is just 1 ohms times the I of t that we have. What will be the voltage across the curve for the voltage across the inductor? Anybody? Straightforward KVL, right? So this voltage plus this voltage has to be equal to 10 volts. So whatever this is just going to be the inverse of it in some sense. Right? So it's going to start off at 10 volts and then go to decay to 0. So that sum of these two will always be equal to the 10 volts that's available across the source. And the polarity of this is going to be again positive here, negative here, the way I've drawn this chart. When I open the switch, what is going to happen to the polarity of this voltage? It's going to remain the same. It's going to flip. What was it?
It's gonna flip.
It's going to flip. Perfect. So in this case, the current was rising, right? Our current waveform, looked at it, it was increasing. Every time instant forward, the current was greater than the previous time instant. So di by dt would have been positive. In this case, when we open the switch out, the current is decaying, right? Over a period of just 1 millisecond. So it's decaying pretty rapidly. So the di by dt term would have been negative. So the way where I made the mistake is the delta I would be the other way around. The final value minus the initial value, and that would have given me the negative voltage for the convention, sign convention that I used here. So in that case, the voltage would have ended up becoming negative. The moment the contact is closed, this will become negative. Positive, and the voltage across this would have been 100 volts. And then we have 10 volts across this. Let's assume the voltage across the resistor is negligible. It's going to be a maximum of 10 volts, negligible compared to the voltage drop across the inductor that we are seeing. So this is going to put a huge voltage across this voltage plus whatever little inductive resistor drop is subtracting out, plus the source voltage is all going to appear across the switch that just was opened out. So, okay. So we are going to have a net voltage of about 110 volts, give or take, across the switch. And this is going to cause arcing in our switch. Right? Many of you would have observed this in your house itself when you're running a vacuum cleaner and you suddenly plug the cord out, or you're running a mixer or some kind of mixer, foot processor, whatever, and you pull the plug out, you would see arcing on the wall, right? And the outlet would get charred out. In homes, you typically have arc fault protection, which basically trips in your basement that you'll have to go reset it because the arcing can cause fire. But we don't want to do this again and again and again in a switch, because this is a very large voltage. First, this is a high, it could either damage the switch that we have over a long time period, or it can end up damaging the inductor that we have. So inductor is basically some kind of iron core, a closed iron core, toroid of some sort. And we have copper wires that are packed very close together. And these are typically varnished so that the two turns do not short one another. Right? If the voltage across the turns are very large, then the varnish can puncture and then the turn-to-turn short will appear in your inductor or motor or whatever be it you're trying to switch. So this is not a viable option. Right? We cannot go on using a mechanical switch to close it on and off because of this huge potential that's developed. And it's particularly more worrying when we go to power electronics or when we go to power system grid. If either the PI value is very large, as you would see in power system, when you open a switch a relay or something, you could have hundreds of thousands of amperes flowing in those current conductors, or if this time period is very small. Either of those is very problematic. Right? And this would typically be the case when we have semiconductor switches, which can operate at like 1 microsecond, or if you have gallium nitride switches, wide band gap devices that can go 50 nanoseconds at very high currents. right? So the dV by dt would be enormously large, and that would break down any kind of device that you have here. So what is the solution? What are all the possible solutions? Yep, Ben.
You run a flyback diode that's normally reverse biased.
Right, perfect. Any other answers? This is the only solution? We don't want to take any other guesses?
You could just open the switch more slowly, I guess.
Right, that's a very good answer. There is a reason that we want to open the switch and close the switch very fast, as we'll see in a minute. I'll do a demo. But we want to push this as fast as possible. Right? These are answers. Right. So let's put a diode across this. So what would happen is when the switch is closed, the diode is just basically reverse biased, right? You have positive voltage on the cathode, negative voltage on the anode. That's not going to carry any current. This circuit is all going to operate as if it was just the before case where we didn't have this diode. But it becomes particularly helpful. So initially the current is flowing like this. And when we break the circuit, the current has a pathway through the diode so that it can freewheel through the diode. So this is typically called a freewheeling diode. The way it's used in the circuit, right? Because it provides the path for the current to freewheel so that when the switch is opened out, nothing happens to the inductor. There is no sudden spike in the voltage or whatever. So we want to increase, right now we are just looking at a mechanical switch, but our objective is to go to higher frequencies, to switch it very fast, and we will look at the reason why we want to go to faster frequencies. But for now, just take it for granted. And the way we do that is replace this mechanical switch with a electronic switch. It's a power semiconductor switch. So in our case, since our voltage for this demo is just 40 volts, and the current is pretty low, I'm just going to use a very simple MOSFET. There's one part missing to this MOSFET. I'll get to it in a second. And then we have the diode. And then we have our inductor resistor. So this portion is exactly same. The inductor resistor from there is the same inductor resistor here, L and R. The diode that was put there is the same diode. It's just that the switch which connects to the source, I've replaced it by a semiconductor switch, and I've just changed the circuit so that it looks more or less like a buck converter that you would typically see.
A lot of FETs have like diodes already in them.
A lot of what?
A lot of MOSFETs, like power FETs, already have.
Yeah, all MOSFETs have a body diode integrated. Yeah,
Yeah.
that's the missing portion.
Oh, okay.
Yeah, yeah.
Sorry.
So you can get you can either use a MOSFET or a IGBT for power applications. IGBTs you can get without a body diode. MOSFET you cannot go away without the body diode is intrinsic.
I was just curious why you also have an external
We'll
diode.
get it.
Okay.
We won't. So when we have a switch, I don't want to jump ahead though. Here we'll put the diode that's there is going to be useless for the case we are analyzing. But when we look at motors, it will become evident why the diode is very helpful, right? So even if there is no way you can physically create a MOSFET without a body diode, but some theoretical miracle, let's say you're able to get away with without the body diode, you would still want the body diode to be there because it's part of the operational requirement of converters as we'll see in a minute. Right? So this is the structure, and the way this MOSFET works is, let's look at our primary N-channel MOSFET. Just some kind of conductive plate. Needn't be metal. There's also like polycrystalline, silica, and so on and so forth, which are also conductive. So the name metal oxide comes from the idea that the plate here is a metal, and then there is some kind of oxide material, typically silicon oxide, that is separating this layer and this layer, and that's how the metal oxide name comes from for the MOSFET, the first two terms. But it needn't be so though. Most newer variants have these polysilicon, polycrystalline silicon, and then in between there are other kind of dielectric material which are different from silicon oxide that was used in the past. But the name has stuck with this. So the way this works is So this terminal is going to be our source, this terminal is our drain, this terminal is our gate. So our source terminal, sorry. Source terminal, then we have a gate terminal. So when you apply a positive voltage across the gate, you get positive charges on this side. So this is a metal conduction region. This has some element of conduction possible. In between, there is some kind of dielectric material. So what you've created is basically a parallel plate capacitor. Right? You apply positive voltage on one side, there's going to be negative voltages that accumulate on the other side. Right? And once this negative voltage, once you apply sufficiently large enough positive voltage, cross over what's called the threshold point, there would be sufficiently thick enough channel here such that this terminal, the drain terminal, can now connect to the source terminal. Right? These N materials have a lot of electrons, excess electrons compared to the silicon substrate, and the P material have a deficiency of electrons, or you can just represent them as excess holes. Right? Again, if you don't understand the semiconductor part of it, don't worry about it. It's a separate course on its own. Too much to cover in this one. But this is the fundamental idea. So you have a whole bunch of electron bank available here, a bank of electrons available here. And when there is no gate voltage here, this channel are two isolated channels, so there is no current flowing. But the moment you excite this gate, a channel is established, which can now conduct. And the thing is, MOSFET can conduct in either direction. So you can pass current from the source to drain or from the drain to source. Right? It's a bidirectional conduction device. Which is not the same with IGBTs and so on and so forth, without a body diode, right? So the way the body diode comes into picture is because of this channel that we have here. So typically the substrate is shorted to the source during the device manufacturing stage. And this PN channel forms the body diode that's always there in the MOSFET. So a MOSFET, whether you like it or not, always comes with a body diode. If you don't want that body diode, you can get specialized IGBTs that don't have that. Right? So that's the very simple explanation of how a MOSFET operates. The MOSFET that I've drawn is not the structure that we use for power semiconductor MOSFETs. Those are completely different. There are drift layers and so on and so forth to allow for higher potential and things like that, which we don't have to get into, but this is the overall simple basic idea of how it works. Anybody have any questions? Yep.
So if the P channel has a deficit of electrons, where do the electrons come from when you apply that?
So there is so let's say we start off with the N channel here. The reason we put the P channel here, if you put an N channel here, right, this is basically shorting this without any control of the gate. Right? So you need to put some material that has a deficit of electrons, but if you apply a large enough voltage, it can strip electrons that are attached to this material and then take them out.
So there's still some electrons there, they're just not enough. It wants more electrons.
Yep.
Typically.
So typically you would have like a silicon substrate with a boron infused into it. So when you have silicon lattice, it needs 4 more electrons to make it stable orbit. So it will basically form this crystalline lattice with 4 other silicon. But what you would do is infuse like 1 in a million part of boron every now and then. And this requires only 3 to complete. So it would lose out one of the silicon pack, right? So that's where the electron deficiency comes. But it does have 3 electrons within it. So if you apply large enough voltage, those electrons can be stripped out from the valence bond to the conduction bond. Okay? So the energy level can be changed using that. So that's the reason we apply this voltage. And that's the reason that you need some minimum threshold voltage before you can get to the conduction. Any other questions? Yeah.
Use a BJT in power applications?
It used to be used, but no longer, because basically the problem with BJT is it's a current control device. But in power electronics, we typically want to have voltage control on the gate side. So here we can control the conduction of this by the voltage that we apply here. In a BJT, you would have a channel you would have to control using some kind of current source. So what happened is basically they took but a BJT has a very good advantage. A MOSFET has a big problem where this channel that has formed here is basically a resistive channel and it drops a lot of voltage. Right? A BJT, on the other hand, there are some principles due to some drift layer injection and so on and so forth, which makes the resistance of the BJT go extremely small. So there was 2 separations. MOSFET used to be used when we have low voltages and low currents. BJT used to be used for very high currents because the resistance of a MOSFET would be too large for high power application. But then came IGBTs, which were basically a mix of the BJT and the MOSFET. So it has the conduction property of a transistor, BJT, and the gate property of a MOSFET. So once IGBTs were introduced, BJTs have lost their relevance nowadays, right? For at least power applications. Any other questions? Yep.
What's an application where you wouldn't want the internal diode?
So there are, so when we have, let's say, there's this class of converters called matrix converters. And what they basically do is they take any three-phase voltages and convert it to any three-phase voltages, all right? And the power can flow either from left to right or right to left. And the way we accomplish this, there are multiple ways of creating the switch. One configuration in which you can create the switch right? So if I turn on the switch, current can flow like this. If I turn on the switch, current can flow back like this. Right? So the way when this would be applicable is, let's say I have a grid connected motor. Sometimes it's going to behave like a motor, but sometimes you want to regenerate the power. For an example, when we had the elevator case, right? When there is a sufficiently large load on the carriage and people are going from a lower floor to a higher floor, you're putting power into the system. But when the carriage is coming from a higher floor to a lower floor, you can actually extract that energy and give it back to the grid, right? That's called regeneration. And when you want to do that, you want the power to flow in the other direction as well. So you want to have control over the power on both directions. So you can use the switch to turn on this side or this side. But that would be defeated if you had a body diode here. Okay, so even whether you turn the switch or not, the current can flow through this body diode whenever it chooses to. So you don't have the degree of control there. So those are called RIGBT or RGIGBT. Right? But basically without the body diode. So they do manufacture those, but it's very limited though. There are only few applications that would require those.
Would a motor controller?
What was it?
Would a motor controller have something similar like that? Because you would have regenerative.
Oh yeah, this can be a motor controller too, right? This output would be attached to a motor.
Yeah.
Right? The input would be some grid and the output would be a motor, typically even in an elevator application that we just saw.
Yeah.
It would be a motor and then we would have the so. Typically, this is not the converter that we use in a motor. In a motor, we would use an extension of the structure, we'll see in a minute, which would automatically allow for regeneration. This structure is not needed. Right? Even in this converter, there are other ways of creating the switch. So you could have a switch like this with a body diode here, and then you could have another switch like this with a body diode here. Right? So this would also allow you to do bidirectional control. So if this switch is turned on, current can go through the switch, through this diode. If this switch is turned on, current can go through the switch and this diode. In both directions, you have control still. So there are ways of getting around this problem with using the body diode. But the problem compared to this, here you just have one switch, the current flows through. Here you have a switch and a diode, the current flows through. So the losses start to increase. Right? So there are trade-offs between this becomes more expensive to get. This is cheaper to get, but then here you have more losses compared to this one. This has other problems as well. When you go from one direction current to other, how do you figure out how to do commutation and so on and so forth? So there are trade-offs between the different devices. Okay. Any other questions? Okay, so we have now replaced it with a switch. We understand how the switch works, more or less. And we know that the switch has a body diode. Okay. There is another diode in the bottom to allow for freewheeling. So there's a bit of a problem with the structure that we have here. The thing is that the diode that is here, that drops quite a bit of voltage. So in a power diode, that can be anywhere between 1.2 to like 1.3 volts, which is a lot. Think of it like if you have a 100 ampere current flowing in this converter and you're dropping a volt across the diode, right? The power that's dropped in the diode is about 100 watts. And these are like tiny, tiny devices. So that bulb on the table, that lamp that we have is a 60-watt lamp, right? And those of you who have used incandescent lamp in your basement or something, you know how hot that lamp gets, even if it operates for a short period of time. Compact that all into a tiny, tiny substrate, which is probably 2 mm by 2 mm in size. Okay. So the heat coming out of the bulb is going to be concentrated into this particular area. How are you going to take out all of the heat? Right. So when you get to higher and higher current, this structure becomes a problem. So what can we replace it with? Is there anything else that has better conduction properties? Yep.
A second MOSFET.
A second MOSFET. This can just be replaced with another MOSFET, and the MOSFET again has a body diode that there's nothing you can do about. But the advantage of putting another MOSFET is, if you go back to our diagram of the MOSFET, once you put sufficiently large voltage, this is basically like a metal conduction channel. You have a whole bunch of free electrons, whole bunch of free electrons, whole bunch of free electrons, and they're just going to conduct quite well. Right? So the drop across the MOSFET is much lower than the drop you would, it's of course not as good a conductor as a metal, but it's a relatively much better conductor than what we can get with a diode. Right? So we want to replace this diode that we have with this switch, which is both a diode and a MOSFET combined. All right, so we have a switch on the top, switch on the bottom. Is there any other solutions? This introduces its own problem, right? Because we need to know how to control this now. Previously, we can just turn this on and forget about it, but now we need to figure out what to do with this switch as well, how to turn this on. When this is on, what happens to this, and so on and so forth. There's a much easier solution. What diode has a very low voltage drop across it? Yep.
Schottky diode.
Schottky diode. So you can replace the previous diode that we had with the Schottky diode, which is basically the cathode channel replaced with a metal instead of a semiconductor, so that the drop across that becomes very tiny. So instead of drawing the MOSFET again, I'm just going to put a switch there. But there is a special class of diodes called Schottky diode. Let's just fill it. This has very low voltage drop, around 0.2 to 0.3 volts. Right? So somewhat better and more manageable than what we can get with a regular diode, regular power diode. So this has a much better characteristic, and it's easier to control because now we are back to just having to control only one switch instead of having to control two switches. So what is the limitation of a Schottky diode? Yep, John.
Question actually, given the lower drop, is there ever a reason to use a regular diode over a Schottky?
Yep, we'll get to it. What is the limitation of a Schottky diode? That'll be the answer.
Leakage.
What was it?
Leakage.
Right? What is the limitation? Leakage current is higher, but there's another limitation.
Breakdown voltage.
Breakdown voltage. So typically you can't find a Schottky diode with a breakdown voltage greater than 100 volts. Okay, so that's where the limitation comes. So when you have a high voltage application, let's say 480 volts or 400 volts, 600 volts, DC burst or something, there is no way you can put a Schottky diode in those applications. So you would have to go to a power semiconductor diode at that point, right? So low voltage applications with a decent amount of current, you can always replace it with a Schottky diode. It makes life simple because you don't have to worry about how to control the other switch. But when you get to high voltage application, you only have two options. Either you put a diode which has quite a lot of power drop across it, which then you'll have to handle. Thermal management becomes a nightmare, or you replace it with a switch and use the switch. Anybody have any questions so far?
So with the second switch, you're essentially just putting it there for the diode?
No, not for the diode. We need to turn the switch on,
Okay.
right? Because the body diode behaves exactly same as a regular diode. It is of no use at all. So the characteristic of this body diode is exactly same as if you have an external diode. So you want to turn the switch on. So when the switch is off, you want to turn the switch on so that the current goes through the channel of the MOSFET and not through the diode, the body diode, right?
Yeah.
But that body diode will now play a very critical role. Without that, we'll get into a lot of trouble, as we'll see in a second. But we want the current to conduct through the channel, not through the diode. Okay? Any other questions? So one of the problems that we have, now that we have put the switch, okay, this is the same switch that I'm drawing here. So let's say I turn the switch on and the current here builds up. So this is, let me call it switch A, and this is switch B. When I mean switch B, it's the complete unit, including the body diode that's part of the device itself. Sometimes called parasitic diode, but that would mean it doesn't have any use. It's a detriment, but in our case, as we'll see, it's very important that diode be there. So switch A, switch B. We are going to be looking at the current through the switch in both cases. So when the top switch is on, the current is going to build up through this, and it's going to do the curve exponentially increasing and then settling down. But let's assume it's somewhat linear looking, and then it gets to our desired value. It stays at 10 ampere. During that time, let's not worry about what happens in this section for a second. Or yeah, let's assume the current was initially 0. I of t equal to 0 equal to 0. So this would have been 0. That's also a problem. The minute I turn the switch off, right? How do I turn the switch off? Reduce the gate signal to 0. Right? Typically, you want to take it negative as well, but let's assume it goes to 0. The current is going to start to die down. But the problem is this current cannot instantaneously go to 0. There's charge carriers that are present in the channel that was previously established. Right? Once you start reducing the gate voltage, the charge carrier has to dissipate because it's a capacitive element, the gate that we saw. So whatever charge was present there must be cleared out before this conduction would start to cease. Yep, Zach.
Maybe a dumb question, but why are the gates unconnected in your drawings?
Why are the gates unconnected?
You know, like on the MOSFET, like there's nothing going into the.
Oh, this is the gate that needs to go double. So this would be controlled by some kind of microcontroller or something.
Okay.
Okay. It's a little bit more complicated because you need some kind of isolation between the microcontroller and the top switch and so on and so forth. Right? We don't want to get into those details, but the idea is basically somehow you apply some voltage on this gate with respect to this source terminal. If the voltage is large enough, this will start conducting. If this voltage is large enough, this will start conducting. Right? But yeah, there are other circuits that goes on after that. This is just the converter role. Any other questions? All right, so once we turn the switch off, it is going to take some time for the current to go down to 0. Okay, and this is again extremely over exaggerated. Typically less than 1 microsecond, and MOSFET it's even faster. IGBTs, high power IGBTs will typically be around 200 nanoseconds or so on and so forth, or 1 microsecond. MOSFETs are typically for low power applications, silicon MOSFET. So those will have much faster switching time periods. So the current is going to take a little bit of time for it to go to 0. In that time, the inductor current was previously 10 ampere, right? So as this current goes to 0, what happens to the other portion of the current? What is the pathway for? Yep, I say.
So it's going through the body diode, switch B.
Perfect. So we haven't turned the switch on yet. So this switch is the one that's on. So switch A was previously on. The gate signal, VG of switch A, and let me draw the gate signal of switch B here. So this is 0 volt VG of switch B. VG of switch A, gate voltage of switch B, and this is 0 for that. Right? So switch B is still off. Now we turned off switch A here, but for the channel to clear out and to cease conduction, it takes a little bit of time. So during the time, the current starts to fall down. But the sum of the current coming from here and the sum of the current coming from here must be equal to whatever the inductor current is. Right? The inductor current cannot suddenly disappear. So what does the current do? A portion of it splits and goes into the body diode of the bottom switch. So it starts to build up and get to 10 ampere during this time period. So that if you take the sum of this current plus this current, that would always be equal to 10 ampere that's flowing through the inductor. Right? So that's the reason we use that. That's the reason that the body diode is quite critical. Calling it parasitic is somewhat of a disgrace because it is actually quite useful what it's trying to do there. So without this body diode, what would happen is we would be forced to turn on the switch right away. Because again, we know that the current cannot be interrupted. So when this switch turns off, this switch must be instantaneously turned on. But there is a problem with it because when the switch is turned off, we see that the channel hasn't cleared yet. And if we attempt to turn on the bottom switch before this channel has cleared, we have created a condition called shoot through, where the DC voltage is directly shorted to two switches. Okay. One shoot through. So until the first switch channel clears, you want to wait to turn on the second switch. Before that, you turn it on, you're basically shorting the DC bus voltage, which would almost instantaneously damage our switch. So this time period in between, where you wait for one switch to turn off fully before the second switch is turned on, what is the time period called?
Dead time?
What?
Dead time?
Dead time. Right at the bottom. So that's called dead time. So in your microcontrollers, you would typically have some PWM module or something where you can say that depending on the switch that you have used, the data sheet will tell you how long it will take to clear out the charge and turn off, turn on times. All of those are given depending on various operating condition. And then you'll program it into the controller that before one switch turns off and the other switch turns on, there should be some amount of time where both switches are off. Right? When both switches are off, the diode is the pathway that it conducts to. Right? Still, the top diode is yet useless for us as of now. But it will become useful a little bit later. But for now, only the bottom diode is useful. But why do we want to turn on the bottom switch? Bottom diode is anyway conducting. Why do we want to go to the switch?
Lower losses.
Lower losses. So we could have left the switch completely turned off and continued conducting through the body diode. That would be fine. But the purpose of putting the switch in the first place was to reduce the loss that we get to the diode. Right? So we want to turn the switch on as soon as possible, but not too quick. If you turn it on too quick, you'll go through shoot through. If you turn it on too slow, you'll end up with a lot of losses. Right? So it's a fine balance as to how you choose the dead time. Anybody have any questions so far? Anybody confused? Anybody want me to repeat it? Right? So anybody know what the name of this converter is?
Synchronous buck converter.
Synchronous buck converter. There's one component missing to make it a buck converter. It's called a synchronous buck. So that's all a buck converter is. So buck converter would have been a diode at the bottom, switch on the top that we already saw. When you have two switches, that's called a synchronous buck converter. There's one component missing.
Output cap.
Output cap. So you just put a capacitor here and it becomes a synchronous buck converter. As simple as that, right? But in our case, we don't need that cap. So look at a quick demo. Check if there's anything else in the information. Right. So we have to have a. So what we have on the table here is basically this arrangement where we have these two switches and the lamp. Load lamp is typically modeled as a resistor. So you can think of that as a lamp. But the tungsten filament and the whole bunch of wiring and the cable, all of those going from the inverter and so on and so forth, that has an inductive effect. So we are basically modeling the same thing that's there on the table. And we're only looking at RL loads because when the motor, when it typically operates in and around the fundamental frequencies, desired fundamental frequency, it does behave like an inductive resistive network, right? When you go to very high frequencies, everything becomes capacitance, but that's not something we're going to be worried about. Okay, so on the table again, I have the power supply, I have that black box. So now we know exactly what's inside the black box, right? It's basically just this DC bus voltage, which is 40 volts, connected to these two switches, right? And I can keep on adding more and more of these. So right now, we looked at only one. So instead of that switch, let me draw it like this, just to make it simple. So going forward, I'm going to use this symbol, which means this whole MOSFET. So whenever I use the symbol, it means it's a switch and a body diode combined together. All right. So the box that you see in front of you has just a whole bunch of these repeating sections. And it has 9 of them. Right. So those are the 9 terminals that you see outside. So let's go ahead and put some voltage on this and see how it behaves. So once I turn this power supply on, it'll be pretty hard to hear anybody from the audience side. If you have a question, you'll have to say it out loud. Please don't fall asleep. So this is the model that I have. So what this basically does is, as I start increasing the slider here, it's going to increase the voltage that's available, the amount of time the switch is on and off. So there are two things that we are trying to control. There are two things that we are trying to control. So we are trying to control how long a pulse is on and the duration of a pulse, right? So if I increase the slider controls how long this is on. Alright, so if I keep pressing on the slider, that basically increases the amount of time the switch is on. So, right, and this itself is the total time period, T period, and this is equal to 1 divided by switching frequency, FSW. Or if you have these repeating train of pulses, you can basically get the switching frequency of the converter by figuring out how long the cycle lasts, a full on and off cycle lasts, and that would give you your switching periods, switching frequency. And this itself is the on time period, T on. And this time period is the T off. T period itself is T on plus T off. So we're going to do two things. First, I'm going to increase I have some set frequency, and I'm going to keep on increasing this duty cycle. And then what I'm going to do is I'm going to start increasing the frequency, or basically reducing this time period. Right? Everybody clear on what we are doing? Right? Okay, so I'm initially just starting off at a very low switching frequency, about 0.5 hertz. So it's going to blink once every 2 seconds, right? A little bit close to 0.5, whatever the closest value it can generate. Hopefully it starts blinking. Right? Everybody seeing it blink? Okay. So if I increase the frequency, the flicker rate is just going to increase. Oops. So let me just change it to 5 hertz. Right. So again, the slider is increasing the on period. The setting that I just changed, that is increasing the frequency, changing the frequency. So it's blinking faster. Right. At what point do you think you'll stop seeing the flicker? Yeah.
10 hertz.
10 hertz. Right. Why 10 hertz?
Some line.
human eye can't update soon enough.
All right, what is the term called?
Persistence of vision.
Persistence of vision. Anybody has any other answers at 10 hertz or? What frequencies do the old movies used to rotate at?
25 to 30.
25, 30. So about 24 hertz was the value they used to use. So let me, so everybody, so the persistence of vision is at 22 to 26 hertz. Varies a little bit here and there, but on an average for most people it's going to be about 24 hertz. So everybody thinks that's the persistence of vision at which we won't be able to see the blinking. Right, let's go ahead and try it. So if I go to, let's say 24 hertz and program it, you should definitely not see it blink. Those of you watching it later on the video, you might still see some flicker because of the camera refresh rate being different, stroboscopic effect. But those of you sitting here should not see any flicker. Right, everybody confirm? Nobody's seeing the flicker? Unless you Superman or something? Everybody else, all right? Okay, but let me see if the persistence of vision is correct though. Let's try 15 hertz. So we should see blinking at 15 hertz. Many of you have done this maybe in like a science museum or something where there is a mechanism where you can rotate. On one side there is a cage, on the other side of the plate there is a bird. And if you rotate it fast enough, it will appear as if the bird is inside the cage, even though those are on two different sides. Right? And the frequency at which you need to rotate would be exactly 20 to 24 times. Right? Below which you'll clearly see them as two distinct objects. So we should see it flicker because it's at 15 hertz right now. Anybody still seeing it flicker? Somebody in the front, Donovan, do you see it flicker? No. Anybody want to give me a reason as to why we don't see it flicker?
Would it be like the incandescent light stays like illuminated a little bit even after it's off?
Right? Because of
I don't know, heat.
pumps.
Inertia?
Perfect. Thermal inertia. So this is a very important principle that we use again and again in our control system design. Let me make sure I stop share. I actually record multiple times. This. Good morning. All right, so what we have going on is that whenever tungsten we have a filament coil and we pass some current through it, right? And it heats up and it takes some time for the heat to dissipate away. Or basically the temperature to die down to low enough value that we don't visually see it anymore, right? In fact, most of the energy that's spent in the incandescent lamp, if you touch it now, it should be quite hot, is basically in the thermal area. There's only 5 to 10% of the energy that's actually used in the visual region of the light spectrum. So it's quite inefficient. That's why we want to move to, that's why we have moved to LED lamps everywhere. But that also means that once it heats up, it takes quite a bit of long time for the temperature to go back to a low enough value that you don't see it anymore and goes to infrared region, and then even lower and you completely stop seeing it. So this is basically same as our equation that we had before. So just the term change. We have some thermal inertia plus some radiative effect, right? That's based on the temperature. So you can model our lamp same as how we modeled our torque in case of our fan, dW by dt plus b omega. There is some inertia there is some thermal inertia here, and then there is some loss here, which is basically what we see as light and feel as heat. And then there is some loss, in that case was viscous friction. So the system is the same. So even after you turn this heat source off, even after this goes to zero, basically the current goes to zero, this temperature is not going to die down pretty quickly. So our temperature rose like this, and then the temperature is going to take some time for it to die down, right? But if you keep doing this fast enough, it won't die down fully. Even before it gets the chance to die down, you have started turning the other sequence on, right? So if you go to a higher and higher frequency, you should be able to not see that flicker at all. And this is an important principle, even though the persistence of vision is much higher than what is happening in the lamp, we cannot see it blink anymore because the inner loop has smoothened the function out. All right, this is the thing we'll use in control system again and again, where we have some kind of two control loops, where one controller is doing current control, and then there is an outside cascaded controller that's doing speed control. We would make some simplifying assumptions about how this operates, same as what we are doing here. If something inside has done it a good enough job and smoothed it out, we don't need to worry about the system. We can assume going forward that we won't see any flicker or anything. Same in motor control, we won't see any pulsation in the speed because of changes in the current and so on and so forth. All right, so this is called cascaded control. Here it's somewhat unintentional. When we design a control system for motors, we will do it, we quite intentionally choose bandwidth and choose the time constant in such a way that this effect is utilized. So we have quite a bit of time. Take a break and talk about something completely irrelevant to this course. So the human eye, the way our vision works, was quite fascinating. We have some lens, and we have a whole bunch of receptors on our retina, all rods and cones, different purposes, detect the intensity of the light, brightness, as well as different colors. So basically, it's a very simple lens, quite a complicated one, but let's simplify it. So light comes through and it gets focused on your retina, and then that signal passes through and goes to your brain and gets processed. This is a very fascinating organ because eye is basically part of the brain. Unlike other organs, eye comes out of the brain during the fetal development. So around three weeks or something, when the embryo attaches from the pre-embryonic stage and goes and attaches to the uterine wall, the embryo's wall collapses and forms what's called these neural tubes, which ends up becoming your brain, your cerebellum, your midbrain, your hypothalamus, and all of those. And this one branches out, breaks down into two more portions, this fetal tube, and this ends up becoming your spinal cord. There's a tiny portion that forms on this neural tube, which is basically what all of these becomes the brain, except for the final section, which becomes your spinal cord, which the whole thing is the central nervous system. But this tiny thing branches out of what is effectively going to become the brain and comes out and becomes the eye. Right? So it's as if the brain wanted to see the world and then figured out a way to see the world. Right? It's very poetic, but it's not the reality though. It's just that evolution is very brutal. Things that then develop those ended up not having successful competition with things that evolve those features quite randomly. Right? There is a big flaw in this design though, if it is a design. Many of you would have done this test in your doctor's office, or you just do it because you're bored. You take a pen and you close one of your eyes and try to move this pen. At some angle, the tip of the pen would not be visible at all. Right? So if the tip of the pen is in such a way that the light ends up falling on this region where the optic nerves all collect and go to the brain, you can't see anything. That's called the blind spot of your eye. Right? And there should be only one blind spot. If there are more, there is a problem that needs to be addressed. Your ophthalmologist will do those checks. But so this is the problem though with the human eye. Because of the way these rods and cones are, the rods and the cones are present, we have these cells which collect the light and make some inference. But the wiring for these come from the top and go back. So there has to be a spot where there can't be any rods or cones, which is basically a blind spot because the nerves comes out of it. But interestingly, when you look at an eye of an octopus, it has gotten around this issue. It somewhat intelligently figured it out to place the rods and cones outside so that there is no blind spot inside. Right? So irrespective of where the light falls, you'll be able to see every single point. This is kind of the argument given by people who are against intelligent design and who are big proponents of theory of evolution, that if somebody had designed it, this is a very bad design, right? Anybody could have just flipped it around and created a much, much better design just by changing the sequence of events. This is even more interesting because the octopus and humans, the evolutionary chain of octopus and humans branched out 500 million years ago. Before there was any DNA inscription to recommend anything of this development of an eye or anything, right? So 500 million years back, none of the species that we branched out of or octopus branched out of had anything about eye in their DNA sequence. But yet two different species that branched out much, much early in their time scale developed the same set of features even though they don't have the same DNA sequence. And this is called convergent evolution, where the need for something is so much that the evolutionary pressure is so large on the species that two different species which have no similar bearings yet develop exactly same features that would make them successful. A lot of other things have this the kind of evolution. For instance, bats and insects and birds all have flight, even though evolutionary they branched out much before flight was introduced in the species time scale. Right? So there are certain developments which are very critical and crucial that multiple species evolve at the same time. Right? So let's get back to the subject at hand. So we want to analyze how our voltage that we just created, this on and off voltage, when it goes to the motor, what is the effect it's going to have on the motor? So before that, let's try to break down this waveform that we have. So this is our waveform. So when I turn the switch on, the voltage was 40 volts. Let's just call it VDC. When I turn the switch off, the voltage across the lamp or the motor or whatever I have connected across the terminals goes to 0. Let's say this time period is 1 second because I want to make my life easy. But in the homework that I'm going to give, I'm going to change this time. There's the on period, there's the off period. Right? We are going to define some term called duty cycle. D, which is equal to T on divided by T on plus T off, which is same as T on divided by T period, time period. Right? TPRD is this 1 second that I've drawn here. But again, this won't typically be 1 second because 1 second you can just use a relay or electromechanical switch or some sort. Right? But we are going to use power semiconductor, so the time period will be let's say 1 by 10 kilohertz, or if you're using GaN, you could very well do 1 by 1 megahertz, if you're using a DC-DC converter with low power and so on and so forth. So it's quite small, the time period in a real world situation, right? So when I say I'm changing the duty cycle, so when I was actually increasing the slider, what I was doing was increasing this duty cycle. So when the duty cycle is 0, the on time period is 0, it's fully off, you don't see anything. When the duty cycle is 1, it's fully on, there is no off. Right? So you see the lamp fully on without any flicker. So duty cycle has a range going from 0 to 1. Now let's say the duty cycle is 0.5. What is my output voltage going to be? Was it
20 volts.
20 volts? So our average output voltage is going to be equal to our duty cycles times VDC. So that's 0.5 times 40, which is equal to 20 volts. How do you mathematically prove that it's going to be 20 volts? It's quite intuitive that average is going to be 20. Now, what is the mathematical setup that you would use to prove it to be 20 volts?
Just RMS.
No, not RMS. What is the other one? If you use RMS, it will become a bit of a trouble.
We're using a straight average.
Straight. Okay. So how do you do the average?
Integrate over time.
Integrate over the time. So this time I'm using 1 second just for the simplicity. But again, I'll give it different. Divided by the time over which you've integrated. Right? So if I integrate this, half of the time it's on, 0 to 0.5, it's 40 volts dt. Rest half of the time it's 0, 5 to 1, 0 dt, whole thing divided by 1 second. Right? If you integrate this, this becomes 40, 40 times 0.5 becomes 20. Right? So, or if you want to derive it for a generic case, you can just put duty cycle times the time period that you have, TPRD. This would be duty cycle times TPRD. So it'll be 40 times duty cycle times TPRD time period divided by time period. So this cancels. So you're left with 40 times duty cycle, which ends up being in our case many volts. So is this the only component? Can I resolve it into other components, the voltage that I have there? How many of you have done Fourier series? Oh, everyone. Right. How do I find out the other components? Anybody remember? All right. So what does the Fourier series say? You know, you guess.
You can sum up any repeating signal with sine and cosine.
Perfect. So the critical term is repeating. If you have a repeating sequence, you can express any signal f of t as a sum of discrete set of sines and cosine. Whether you use A with sines, B with sine, or it really doesn't matter. But one of them is sine, the other one is cos, and so on and so forth, all the way up to infinity. So the idea is if you have a discrete set of, if you have any repeating signal, you can resolve it into some DC component plus a sum of sines and cosines, which are just multiple of the fundamental frequency that you're trying to analyze. Is this always true? Can any signal truly be resolved into sum of sines and cosines?
Periodic.
It has to be periodic. Okay, sorry, let's assume it's periodic repeating signal. Can any periodic repeating signal be resolved into sum of sines and cosines? Is convergence always guaranteed? What's the condition for convergence? So there is one very critical exception to the case. So when Fourier presented this back in the early 1800s, it was denied publication. He had to work on it for another 15-20 years before it was accepted for publication because Lagrange and Laplace and others felt that it wasn't rigorous enough as analysis. So he just said that the idea that signals can be resolved into periodic signal predated Fourier much earlier in the BCs. Itself, people had some ideas that based on looking at planetary motion, they had a feeling that you can resolve it into some of repeating signals. But Fourier was the one who came up with the idea that all these signals can be resolved into some of repeating trigonometric periodic functions, sines and cosines. But it wasn't accepted for quite a bit of time because the analysis he did was not rigorous enough. Now the constraint Dirichlet test, Dirichlet Jordan, in our case, it's all real values, so we only worry about the Dirichlet constraint. Anybody remember from your first year math class what the Dirichlet test is? Right, so Fourier analysis is only applicable for repeating continuous time signals. Okay, is our signal continuous? Does our signal fit the definition of being continuous? What is the test for continuity?
Signal from the left equals to the right equals in the middle. Something
Right?
like
How do you mathematically define that operation? Limits or other way to test it?
the derivative, first derivative test.
Perfect. So the continuous function is always differentiable at all points. Is our curve differentiable at all points?
In reality, yes, but that one's not.
That one's not. In theoretical, when you have a square waveform, there is a jump discontinuity in the signal. And this is very important because it was about 30 years before people figured out the issue with using Fourier in cases where jump continuity exists. So whenever this kind of jump discontinuity exists, the Fourier does not guarantee convergence. Every other point, if you sum up to infinite signals, you would get exactly the same waveform except at these points where the jump discontinuity happens or any form of discontinuity happens in our equation. This is where Dirichlet test comes into picture, where he puts down the constraint that if such a discontinuity exists, Fourier still converges, but to the average of the two discontinuous value. Minus d of x plus divided by 2. Okay. So many of you would have seen this very intriguing graph. Part of your Fourier analysis assignment in your math class, you would have, the instructor would have asked you to sum up the sine waves up to like 10 or 15 or whichever order and then plot it. And sometimes they would ask you to keep on increasing this order up further and further, right? 100, 200, 300. No matter what you do, you would always see this waveform. Where these two peaks somehow don't go back and go to the same value as the step top and the step bottom, right? And you can take infinite number of signals and add it. Theoretically, you can show that this will never converge to this value because convergence is only guaranteed at points where there is continuity. Here there is a discontinuity, there is no convergence guarantee. But Dirichlet tests say that if you take this value, sum it up in the average, that would be same as this value's average, which is this midpoint, which would be this midpoint, right? So that's the only constraint. There is a very interesting story which we'll get to next week on this. But for now, let's continue with the math. Maybe you want to tell me how I'll get the first harmonic content, the sine of omega t, a1 sine omega t. Sine n omega t and cos n omega t form a family of very special class of functions. What are they called? Orthogonal functions. Orthogonal functions. Do you remember the properties of orthogonal functions? Do you remember any other class of functions that are this property? Right, so whenever you have an orthogonal function, some function f of t and another function g of t, repeating function, you integrate them over one cycle, the inner product f of t times g of t. They would have to be equal to 0 if f of t is not equal to g of t. Right? So what that means is all of those values that I have, sine omega t, sine 2 omega t, sine 3 omega t, these all form the basis vector for an orthogonal vector space. So what that means in simple terms is that if I take the integral of sine omega t times sine 2 omega t over one cycle 2 pi by omega. This value is always going to be 0. Right? You can plug this expression into Mathematica and it will give you the answer. Again, for homework, anywhere I ask you integration or something, you can just use Mathematica. Don't go through the process of having to solve it by hand. It's useless. But again, same if I do sine omega t times cos omega t, that would also give me 0. Alright, so this is a property of orthogonal functions. And another function that shows this that you would have read about is the Chebyshev polynomial. Right, the polynomial with the leading coefficient 1, which has the lowest absolute error when you try to curve fitting. So this is a critical property, which is what we are going to be using to find out that sine omega t component. But when we do integral of sine omega t times sine omega t, that will not be equal to 0. Right, so this integral is 0 for all cases except when f of t equal to g of t. And this should be quite obvious, right? Because when you do sine of x times sine of x, you get sine square x. When you have square of something that never goes to 0, it never goes negative. So the integral of it is always going to be some positive non-zero value. So with that in place, how do I figure out the A1 coefficient? Anybody want to take a guess? So let's say your Fourier sitting there and trying to struggle finding out the solution for the Fourier series. Yep, Thomas.
I just have a question. Your magnitude, like in front of each sign, would also have to be the same, right?
Magnitude in front of
So
what?
if you have like 1 sine omega t and then 2 sine omega,
Doesn't matter. It'll go to 0. So anybody remember what's the 1 sine omega t times 2 sine 2 omega t or sine omega t?
2 in front, like as an amplitude. If one amplitude's bigger than the other, wouldn't there be like space under the curve?
So if you had sine omega t and then the other one was sine, right?
Yeah.
This would not be 0 because again I laid down the constraint here. Sine omega t times sine omega t, respect of what we have.
So the argument.
This won't be 0.
Okay.
But if you had, say, 2 sine 2 omega t, irrespective of what magnitude you put in the front, it will be 0. Right? So there's a very easy way of visualizing this. So let me just go to Google, sine of x times sine of 2x. Used to show up now. Right, so if you look over one cycle, it's always symmetric. Right, irrespective of if I say I had 1 here, 2 here, this just becomes 2 sine x times sine 2x. That would just increase this curve on both sides equally. Right, so irrespective of what kind of products I have, so I can do, let's say, cos x. Cos x is very easy to visualize because we know that it would end up being some form of sine 2x. Right, so right, again, if I do it over one cycle, it will end up being 0. The only time this won't be 0 if it's f of x equal to f of t equal to g of t. So if I instead put sine of x there or sine 2x, in those cases, the integral would end up being non-zero. Right? So this is property of all orthogonal functions, irrespective of what scaling factor you use in the beginning. The product term really don't matter, it's just the function themselves. So only if the frequencies is exactly the same, the integral will be non-zero. If the frequencies are different, the integral will end up being 0. Right? With that, see, let me just take one more minute. Whatever you have to leave, that's absolutely fine. The video is recorded, so you watch it later. But the key concept is, so the idea is if I multiply whatever function I have here, this is so if I multiply this function f of t by sine omega t, right, and try to integrate, if I integrate sine over one full cycle, what is the value? The sine wave, right? It has equal positive and negative components, so the value is going to be 0. If I integrate the dc times sine omega t over one full cycle, it's going to be 0. If I integrate sine omega t cos omega t over one full cycle, it's going to be 0. If I integrate sine omega t sine 2 omega t over one full cycle, it's going to be 0. Every single term will end up giving 0, except for this one term which will become sine square omega t. Right? So I can integrate the term on the left, integrate this term on the right, I'll get the A1 coefficient. So the same thing I'll do. If I want to figure out the coefficient for say Bn cosine omega t, I multiply all of this expression by cosine omega t and integrate every single term on the RHS will go to 0 except this term. And on the LHS, all I have to do is integrate this from 0 to my cycle time period times cos n omega t. Right? And that would be same as integral of this Bn cos n omega t, and then I can get Bn coefficient. This we are done, we'll continue on Friday.